Hello everyone, good evening. We're back here again at ARS Stream PDMP. We've had our first section in Excel today. This night we have our trainer for SPSS, Miss Machi Davis Obodo, who is a statistician and data analyst. Today we'll be completing hypothesis testing and also looking into chess square tests. Miss Machi, the floor is yours.
I forgot I was mute. I was on mute. Okay, good evening, everybody. So, the class was supposed to be 1 hour. That's like 7 to 8, and my plan was keep it to that time. I'd already cut all my things short so that people that are going to watch World Cup can watch it. Anyways, but we can start. I don't the things are not. I already did a lot of explaining in the last class, so we'll just go right into it. I had sent just a few minutes before the class started a data set to the group that we're going to be working on. So, and I've already done a little bit of work on the data sets because in the last class I showed us how to work on data sets, and I don't want us to go through that route again. I would send in an assignment and we can play with that, but I don't want us to go through that route again. So I'm just going to share my screen and we're going to dive right into working with the PSPP instead of um instead of going through trying to. I've already coded data. All right, so share my screen now. All right, please tell me if you can see my screen so that I know that we're on the same page. Can you guys see my screen? You can, if you don't want to talk, you can just like
Yes, 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 yes.
okay, thank you. Great. Okay, so I'm going to import the file that I sent to you guys, and it's good if you like do it with me so that um they're not too confused. Okay, I'm going to import the file that I sent. I was working on it before, so it's easy for me to find it. But when you download it, you have to find where you downloaded it into. That would help you. But since I was working on it a few minutes ago, mine is just here. Okay. We already basically went through these last time, so we already know how to get our data into this. Looking good. So data would look, and we can apply. Okay, so our data is now here. It's loading and it's here. And basically, okay, let me show you what it looks like in the Excel file so that we see basically what data is saying. So this is not the correct one. Hey, God. Anyways, it doesn't matter like that. Okay, so this is more or less what the data would look like what it looked like when I generated it. So it has the ID numbers is a data from radiography data taken. It's not a real life data anyways. I just generated it because it was difficult to find a real life data, but I think it would do. So the questions, the more or less the headers are age, gender, hospital type, image, imaging modality, years of experience, radiation, safety training, PPE compliance, knowledge of knowledge score, waiting time of patients, and patient satisfaction score, and contrast reaction. Okay, so I'd already coded that, and that's why we were seeing it as numbers in my PSPP because I had coded it. And what I did was I had written the codes down. So we are going to tell SPSS what we could, like we did before, what those codes are, more or less. Okay, so ID, age, doesn't matter, gender needs one. Okay, so for gender, I had coded what did I do it? I coded female as 2. So sorry, it's supposed to be 1 and male is 1. Then I coded 2 and value label is female. Right? Yes. Okay. So that's that. So I can say okay here. Then for hospital type, I had 1 as private hospital and 2 as public. Basically. Then for image modeling, image modality, I'm not be sure what that is. For image modality, okay, we have CT and we have MRI and we have X-ray and we have ultrasound before X-ray. I kind of did it alphabetically so that I wouldn't get confused. So here we can have 1. 1 was CT, 2 was MRI, 3 is ultrasound, sorry, 4 is X-ray. Okay. Yeah. So years of experience, that one is numerical. Radiation what now? Radiation safety training. So the question was more or less, performed, have you done a radiation safety training? And it was yes or no. So my 1 was yes and my no was 2. Okay. Then same thing for MPP compliance. Okay. Mm. Please, if you're lost, you can let me know. And what I'm doing is just code, like trying to see what the numbers mean so that SPSS interprets it well for those of us that were in the last class. Okay, so PPE compliance is basically personal protective equipment, where you compliance with the personal protective equipment that we're giving. Then the next one is knowledge score, which is numeric, so we don't need to code that. Waiting time, numeric. So the next one is contrast reaction. You can code that. It's still yes or no, so it's sorry. Right. Okay, sorry about that. So yes, here is 1 is yes, and 2 is no. Right, so basically we're done with that. Okay. So we are basically dealing with chi-square and with we're dealing with chi-square and we're doing independent sample t-test, right? Because in the last class I was saying how there are different kinds of t-tests, but the important one, the one that concerns from this research that I did, the one that we most times you would use in your research is the independent t-test, because in that case, what are you doing? You're doing a nominal data versus a scale data. And I had said in the last class that a nominal data is the data that has categories like this yes and no that we had, or male and female. Um, they are nominal data. They are data that have categories, while scale are mostly, no, not mostly, they are numeric data. So when you want to um figure out how this nominal data, this characteristic, this categorical data is associated with your scale data, you use an independence test basically. Then for a chi-square basically shows, I have a little PowerPoint here that like that is just very plain. A chi-square shows association between two categorical data. Um, and what we're going to be doing is to be trying to answer questions and basically see what would make me use a chi-square in a research. So, for example, you want to, from the data that we have, you want to find the relationship between two categorical data. So, from this data that we have now, we have a couple of categorical datas, or data, something like data. Gender is categorical because you can divide it into male and female. um what else? Hospital type is also categorical because it's private and public. um Imaging modality is also categorical because it can also, like, it's not is it doesn't have like a an order in itself, like, oh, this one goes before this, but it's also in categories because you can't, like, it's not skill, it's it can be divided. So x-ray, MRI, ultrasound, CT, and tell you, okay, the different types of image modalities, those are what we call categorical data. And yes and no questions are also categorical data. True or false questions are also categorical data. So a a question here from this data that would um more or less need chi-square to answer is something like, is there an association between gender and image modality and imaging modality? um just maybe you want to know what does is there any association, or is it that more males would come to a clinic and ask for, I don't know, a CT scan, or that more females will come to the clinic and ask for an ultrasound? Like, maybe you want to figure that out. What is the relationship? How are gender and imaging modality related? Or you want to know the relationship between gender and the hospital type. Um, are would we see more males in a private clinic than see more females in a private clinic? Or is it the other way around? Are we going to see more females in a private clinic and see more males in a public clinic? So you're trying to see what's the association. Um is it like the, if I take a sample of more of a group of people and I have more males, I'm going to see that most of them go to private clinics. That's what chi-square is basically asking. Um it can also be finding the association between radiation safety training and PPE compliance. So radiation safety training, in the sense that maybe the radiographers in a company are told to take this online training course on safety, and some of them took it and some of them did not take. And you now check, okay, people that took, do they is the okay, so then there's a PPE that they say, okay, you have to dress like this to enter into the lab, or more or less. And you want to now, of course, from the top of your head, you can already say that people that didn't attend the safety training might not know that they're supposed to wear this protective gear to enter into, I don't know, the room for work, or the room for the x-rays. So you're now asking yourself, okay, let me collect data and find out if radiation safety training has any relationship at all with PPE. So that's exactly what chi-square does, and would see it here. So but for independent sample tests, what we are trying to find out is that um what what is the relationship between this nominal data and a scale data. So for example, you'd be asking something like, do public and private hospital differ in the average patient waiting time? So you're like, okay, um you go to a private hospital and collect their average patient waiting time, and collect their patient waiting time and go to a public hospital and collect their patient waiting time. Now, a calculator cannot do that because you're not finding the association between two categorical data. You're not just asking, oh, is this related to this? Does this increase when this increases? No, you're saying that on an average, would I find that the private hospitals have lesser waiting time than public hospitals? Or you're asking yourself that do male and female radiographers differ in years of experience? Um, you want to know, okay, from what I'm collecting, I'm seeing that I don't know, males have more experience than females in this field, but you want to be sure, so you can use an independent t test, independent sample t test. Okay, so now we can go right into it since we've coded this data and see
Sorry,
how we
ma.
can. Yes. Oh, hi.
Sorry, dear. Please, I can you please go over the t-test again when we use it? I didn't get it so well. At least I understand the categorical data and the other one. Just when we
Okay,
use t-test,
t
thanks.
test. Okay, let me also put my slide so that it would help in you seeing it. Sorry. Mm. Okay, so what an independent sample test does is to compare the means of two independent group in statistical terms. That's how it's going to work. So you're trying to find out what how do these two groups differ. Remember, in chi-square, we're trying to find the association. How is this associated with this? But in t-test, you're trying to find where do these two groups differ in the average score. So now, for example, I had given an example of, do public and private hospital differ in average patient waiting time? So what you first collect is, you collect that these hospitals here are private, these hospitals here are public. Those are two groups. But now you're trying to find, do these two groups really differ in their average score, in their average patient waiting time? You're asking the question, do they really differ in the real sense of it? Is it that, oh no, it doesn't matter whether you go to a private hospital or a public hospital, you're going to shall wait? Or that, no, if you go to a private hospital, you're not going to wait, but if you go to a public hospital, you're going to wait. So that's it. So the second one I used is, do male and female radiographers differ in years of experience? So same thing, you're trying to find out, do these two groups of people, and t-tests can only be used on two groups. So now if I have a nominal or a categorical data set that has three groupings or three options, for example, what will I use now? I'm trying to find out if level of education, or rather if level of education, um what would I use as the example now? If level of education has any, do people's do would that level of education in terms of somebody that has a primary education, somebody that has a secondary education, and somebody that has a um tertiary education, does it affect their computer skills, something like that? So I can't use a t-test there because now I'm going beyond two groups. I now have three groups. That's where you don't talk about ANOVA test and the rest. That one is something else. So basically what the t-test is saying is that these two groups, do they really define their average score? Do they what do they really is there really a difference between these male radiographers and female radiographers in relation to their years of experience? I don't know if that explains that.
Yes, ma'am. Thank you very much. It's clear now.
Okay, thank you. Okay, so we can we can what can we do? We can try and see what SPSS has to give us. So the first question I want us to do is there an association between gender and, so we're starting with chi-square tests. Is there an association between gender and imaging modality? That's what I want to see. And how we'll do that is that we'll go to analyze, and we'll go to descriptive statistics, and we'll go to cross tab. Analyze first. Like, just click on this analyze tab. You can see my screen, right? Then you go to,
Yes.
okay, thank you, cross tab. Okay, so for cross tab, you want to, what do you want to cross? You want to cross gender and imaging modality, more or less. And you want to find a statistic, and you want a chi-square statistic. Continue. Okay. So we go here and we see what our output is saying. Okay, so SPSS always gives a summary case, a summary output for you to find out, for you to be sure that, okay, it's the number of data that you put in that it's actually working on. So it tells you the value, like we said in the last class. Then we had also done something on this cross tab table is a descriptive statistics table. So see what happened if we had left 1 and 2 as like without coordinates. We'd be seeing 1 and 2 here, and we'd be asking ourselves, sorry, what is 1 again and what is 2? But we interpreted the coding, so now we have this. So basically, this it just shows you like the percentage of which people said what. So here now, gender, male and female. So it shows that 23 men say that they come to the hospital for a CT scan, like normally. Then 5 men say that they come to the hospital for an MRI scan. And the same like that, 15 say they come for an ultrasound, 11 say they come for an X-ray. And you now see the female count and see the total number of people that come for this and come for that. So if you're seeing this already, you can more or less say, okay, maybe majority of the men come for a CT scan and an ultrasound, but it still shows that more women than men, at least from the sample that you've collected, would come for an ultrasound, because it's showing here that 28 women would come for an ultrasound, while 50 men come for an ultrasound. Okay. Okay, so this is the chi-square test, and in interpreting now, what SPSS does is that um it gives you a table, but more or less you don't need everything on the table that SPSS gives you. What you need is basically more this first line. That's what needs interpretation. These other ones are it's trying to tell you, okay, that the likelihood ratio and the linear bilinear association. That's that it tried to take one male and CT scan, on average, male and MRI, male and ultrasound, male and X-ray, and now gives you the average linear bilinear. But the most important one is the Pearson chi-square test. Does this first one here. Okay. So let me go to the slide so I will see. Sorry, it's back. Okay. Where am I? Okay, so now we have our Pearson chi-square to be 2.94, and our this DF means degree of freedom. Then it shows that it's a two-tailed test, and the value that it gave us is 0.401. Now, what the value that we're going to use to interpret is this our p-value, which is the value that was given to us from our Pearson chi-square 2.94. Now the rule says that, which we would read in this slide, that if p, which is your p-value, is less than 0.05, this is what Pearson formulated in the beginning. that if P is less than 0.05, then you reject the um null hypothesis. But if P is greater than or equal to 0.05, then you fail to reject the null hypothesis. Now, what we didn't do was to say what our null hypothesis is and what our alternative hypothesis is. So, and how do you do that? You get it from your question. The question is that, is there an association between gender and image modality? That's the question. Is there an association between um gender and image modality? So your null hypothesis is going to be that there is an association between gender and imaging modality. But your alternative is going to be that there is no association between gender and imaging modality. That is it. There is an association between gender and imaging modality, and second one is that there is no association between gender and imaging modality. So now remember, if our p-value is less than 0.05, we are rejecting HO and saying that there is, what did I say my HO is again? That there is an association between gender and imaging modality. But if it is greater than 0.05, then we fail to reject the null hypothesis. Okay, so if you go back here, you see that your p-value is 2.94, and that is obviously greater than 0.05. It's obviously greater than 0.05. So that means that what you're going to do is that you're going to fail to reject the null hypothesis. Now, now when you fail to, statisticians or people, when you're doing research,
Sorry,
you
Catherine, please. Sorry. There's a hand up.
oh, okay, so sorry. I am not there, so
Okay,
I'm not.
No problem, no problem.
sorry.
G.
Yes, yes.
Okay, ma. I'm a little bit confused now. I think one of the things they've taught us in this statistics, we were told that no hypothesis is built on the negative, like
Okay.
whatever the question is going to be, it will be on the negative, like there is no association or there is no, as in, it's on a negative. That is how to form the no hypothesis. So
No
my
hypothesis.
question now is, are we free to maybe when you're doing your own, you can turn it around,
No,
or is
no,
it
no.
a basic
Did I
standard rule?
did I swap it? It's standard though.
Yes.
If it is supposed to be, yes, it's standard. No hypothesis is no association exists.
Okay, ma. I
Sorry,
think
I
we
think
swapped.
yes, sorry, so sorry. Thank you for calling. Thank you for
Yeah, I
pointing that.
think you swapped it.
Yes, I swapped it. Thank you. So no hypothesis is like here it says that is there a association between gender and preferred imaging modality? Yes, so sorry. I thought I was saying the opposite. So no hypothesis that no association exists, that there is no association between gender and imaging modality. While for the alternative hypothesis that there is an association exists between gender and imaging modality, right? And I think it's good that we even know the why, because if we know the why, then we somehow don't have to we somehow don't have to, what they call it, guess or cram it. So now it's because when you're like, it's scientists that use this method, and I think one of the, I don't remember it clearly, but scientific methods, the steps, when you take an observation, do an observation and you have a problem and you make your hypothesis, because you've not you don't have a result, more or less, you cannot now claim that something exists. I don't know if you understand. You cannot claim that something exists because you've not run it, you've not done the test, you've not done anything. You're just still making a hypothesis. So that's why your null hypothesis has to be on the negative, because that's like the foundation of your problem. That's foundation of your, and that's what you're working on. That's what you're trying to figure out if it's correct or not. So it's the negative because you're still on the process of uncovering what is actually true. So it's better that it's almost like you're trying to play safe. Okay, there's no association because I've not figured out if there's an association yet. Okay, so yes, thank you. Thank you very much. I'm ready past three now. Okay, so I was saying that if p-value is less than 0.05, we reject the null hypothesis, right? We have rejected the null hypothesis. That means that if p-value is less than 0.05, we're going to be saying that, here's not my null hypothesis again. Sorry about that. We're going to be saying that there is that an association exists. if it is less than. So we are rejecting that, but we're rejecting the null hypothesis, which states that there is no association. So it's more, but um in statistics we try to, what do we try to do? That's what it was. Some people still go ahead and use the term, but a lot of our lecturers and professors that time will tell us that you try to avoid saying that you accept the alternative hypothesis. And I think it's just generally that people like to play safe because, first of all, what have you done in the research is that you've taken your sample from, and probably you've tried to be generous in taking your sample and take it properly, done a good sampling technique, and taking it from a wide range of people. But in in real sense, you never ever take data from everybody, from the whole population. So you take just from a sample. So when you now when you're trying to be, I hope I don't confuse you with this, but when you're trying to report and you sound very certain, it looks as if you went house by house to every single human being you're supposed to collect the data from and got this data, and now the result from all these things you've said is this. But because you took a sample, you avoid words that make it look like nobody can contest this my research, something like that. So that's why they try not to use you accept this hypothesis or something. They just go with you reject or fail to reject. You either reject or you fail to reject. Okay, so I was explaining this p-value. I said that if the p-value is less than 0.05, we reject the null hypothesis. But if the p-value is greater than 0.05, then we fail to reject the null hypothesis, which is more or less like we're accepting the null hypothesis. So now our result here, and the value we're using is this 2.94, right? Yes, 2.94 is greater than 0.05. And since it's greater than 0.05, we are going to fail to reject the null hypothesis. That's that we are accepting the null hypothesis, which states that no association exists. So null hypothesis is basically saying that there is no association between gender and preferred imaging modality. That's that if you probably, like, you don't have more from our cross table, you don't really have a significant number of women that are more than men that probably choose ultrasound, or you don't have, like, it doesn't really matter, the almost like the difference doesn't matter. So anybody can come to the hospital and demand a CT scan, anybody can come to the hospital and demand an MRI, anybody can come, it doesn't matter whether the person is male or female. Now, I'm not a radiographer, so I can't even tell if that result is supposed to be the correct reflection of the hospital. So these people that will tell me, I don't know from, maybe what you've been taught or what you've seen, is, I don't know, this test that we just did now in real life, is it correct?
Okay, ma, I think to start with, I think we're sorting it again because we're failing to accept the null hypothesis. So that's more like we're accepting the alternate, which says that there is an
You're failing
association.
to reject.
So means we're failing. Okay, we fail to reject. What's the difference
Yes.
between fail to reject and you're rejecting?
When you reject, you're saying that,
There is no association, but when you fail to reject, you're saying there's an association.
no, when you reject the null hypothesis, remember that the null hypothesis is the one telling you that there's no association.
Yes.
So when you reject the null hypothesis, you're saying that there is an association.
Yeah. When you reject it,
Yes,
when
because
you
you're saying
okay,
that what the null hypothesis says is not correct.
okay,
Yes,
okay,
but when you
okay.
fail to reject it, it means that you're accepting. I think it's English.
So
If
you
you,
are accepting now that
yes,
there is
you're
no
accepting that there is
association.
no association. Yes.
Okay, okay, okay. But I
Mm-hmm.
think for in real life there is really no association. It's not the male or female that determines which
Better.
which um, imaging equipment that you should be imaged with. Is the disease condition, the patient clinical history that
Mm,
tells which modality the patient should use. So I think we're correct clinically.
I'm the same. Okay. Thank God. Okay, so this data that I generated was not too wrong. Okay, so yeah, so basically that's it. it can be very confusing on most days actually, because it kind of needs a lot of practicing and um remembering what's like the terms for it. But I don't know whether that background I gave on the null hypothesis helps a bit, why it's always negative. And if the whole thing of reject and fail to reject confuses you, you can try to like write somewhere that fail to reject is accept, so that you don't have to, because I think I was even almost confused right now. You don't have to like wonder, okay, am I rejecting, am I accepting, what exactly am I doing? But if you're able to say that when I'm failing to reject, I'm actually accepting something, it's just for want of better terms, like what I was saying, like um try not to be overconfident. That's why um researchers try to use these words that show that their research still has room for to be challenged, that they are not it's not the final say. If somebody comes tomorrow and says that no, I've worked somewhere and I think that there's an association between gender and preferred imaging, they don't have to hold me by the neck and say that I said that they can never be an association between that. So that's why it's like I feel to reject. And you kind of always um mention that it's according to this data that you've collected, the data that you've gone and you've collected from this group of people, that this is the result that comes out from it. Yes, data can be reflected to the whole population, but it's good that people know where you collected the data from, and the true reflection of the data, what it reflects to. Okay, so I think we can do another one. Um, sorry, 1 second. We can do another one, then we go to. I'm coming. I'll share my screen back. Then we go to independency test. Mm, I'm sorry. I'm sorry. Miss Priska, I wanted to know if you. We know we had I think it was you. We had an issue with your PSPP the other time. Like it wasn't showing the second. How did you put it? The second sheet, right?
Okay, I think I put the stuff in the second sheet, but it wasn't saying it or
Okay, so
so. Uh,
um what I had never come across that problem before, so that's why I was a bit confused that day. But I went to research on it, and I think what you can do is that you can try to swap sheets. Let that sheet that you actually want to show be the first sheet there, so that it picks it up. In SPSS, you'd see like a tab for um choosing the sheet, right? But in PSVP, depending on the version, sometimes you don't see that tab. So they said that it's better that you just move the sheet to the first one, so that the application just accepts, collects the first one instead of trying to figure out which one you want.
okay, so there's a button I'll see that I'll swap it and move it to be the first sheet.
You can actually just on your Excel sheets, you can just how do you put it, drag that
Okay,
sheet
drag.
to the first page.
Okay,
Yeah.
okay. All right, maybe I'll try it. Sorry, I'm using my phone now. During the last class, my phone did one thing, and blank. So maybe after
Okay.
now I'll look at it. For now, I'm just on my phone. Hopefully, later I'll look at the laptop and probably get it back.
Okay.
Thank you, Ma. I really appreciate it.
No problem. Okay, so we can go to the other one. Um, share my screen before. Where is it? Okay, good. Sorry. Okay, so the next question I have is um is radiation safety training associated with PPE compliance? Is radiation safety training associated with PPE compliance? So we can do that very easily. It's like the first one: analyze descriptive statistics and cross tab. Then we're talking about radiation safety training. Sorry, let me remove this one so that we are not confused. Radiation safety training and PPE compliance. Then I confirm that my distance is still on chi-square test. And I say okay. Right. Okay. So the same thing, it gives me um um that thing. So it shows that more or less radiation safety training, people that this cross tab shows that radiation people that say yes, they went for the radiation safety training. 83% of them were people, or 83 of them were out of 87. This is the total people. This total number of this 87 here shows that these are the total number of people that sorry, this is the total number of people that I've lost my train of thought. This is the total number of people that said yes to radiation safety training. While but 83 of them did did the radiation safety training were PPE compliant, while 4 of them that did radiation safety training said no, that like it was that they were not PPE compliant. Then we can see from here people that did not do radiation safety training, 19 of them were PPE compliant, and 14 of them were, yeah, like that. Okay. So now to our chi-square test, it shows us that um why did they give me this figure? Anyways, it shows us that Pearson chi-square is 26.85. Figure figure number 1, and the asymptotic this thing is a two-tailed test. Okay, so the same thing for since it's radiation safety training associated with PPE compliance, the null hypothesis is negative, meaning that radiation safety training is not associated with PPE compliance, while the alternative is that radiation safety training is associated with PPE compliance. Now, something I didn't mention before, which I didn't mention it because the two things looked alike or basically have given us the same results, is that when you are doing a chi-square test, you two values, like even like I said, everything on this Pearson chi-square is important, right? Is important. The value, this value, and this degree of freedom, and this asymptotic two-tail test. Now, I didn't mention it before because it was going to give us the same thing, but this 2.94, which is your chi-square value, and this value, if both of them behave the same way, that's if 2.94 is like here, it's greater than 0.05, and 0.401 is also greater than 0.05, then it's a win-win for you. You go ahead and since it's greater than, we fail to reject the null hypothesis. But now there's a bit of difference here, which is why it drew my attention to it. Now, this value here, 26.85, is bigger than 0.05. But now we see that this value here, the asymptotic CM, is almost like perfect. Is 0.0 more or less, and it's less than 0.05. Now the value that really tells you the association level is this your tailed test, this your asymptotic two test. It helps you to confirm that what this value says is correct, more or less. So like I said here, I didn't bother saying that because they were going to result in the same thing. But now here where we have this 26.85 and this 0.0, Here in this one, it's way higher. 26.85 is like, it's almost like why you compare 26.85 and 0.05. But here it's lesser. So we're going to go with this two-tailed value, this significant two-tailed value. So 0.0, this zero p value, this is the p value, is less than 0.05. And remember what we were saying, when it's less than 0.05, we when it's less than 0.05, we reject the null hypothesis. We reject null hypothesis. That means that almost like we're accepting the alternative hypothesis. So since this p-value is less than 0.05, we're rejecting null hypothesis, which is that there is no association between radiation safety training and PP compliance. That's what the null hypothesis was saying. So we're accepting the alternative, which says that there's an association between radiation safety training and PPP compliance, more or less. Okay, so let me go back and clarify myself. So I said that normally the values you're looking at is your Pearson chi-square tests. The likelihood ratio and the linear, they are not very important figures. So, but you have to look at this because if you're solving it mathematically, like if you do the actual statistics, like Baron pen, like this taught us in school, not the system, the values you're going to get is this degree of freedom and this value here. That's the value that is going to come out. You're not going to get this significant value from your calculations, right? So, but what PSPP does is that it saves you. I don't even know if you remember our four-figure table in school that time. Yes. So that our four-figure table now, there's a way that you get values from there. This is the value that this SPSS is giving, this PSVP is giving us now. So now if these two values interpret the same thing, then good for you. But when you find one that the two values are now saying different things, you fall on your tabled value, which is your two-tailed test. I don't know if we get, because normally people will tell you just look at your two-tailed test and forget about this other value. But it's also a very important value. So you look at both of them, and what the two-tailed test does is supposed to confirm your Pearson chi-square value. So when we look at here, we see that it's less than 0.05, and we can now reject the null hypothesis and say that okay, there's an association between radiation safety and PP compliance. Okay, so now we can go to T test.
Okay, so in the two now, I remember in this I did stuff like this. That we used to quote the p-value. P-value is equal to 0.001 or 0. So in this case now, is
Sorry, I
it
didn't
that
get that.
so we used to quote when you're reporting
Mm,
your analysis, we
mm,
used to quote the p-value. So
mm.
in this case now, which one are we now using as the p-value? Here is that one that is in the something to tell. Like in the first
Yes,
case, now it's going to be 0.4 stuff.
401. Yes, is
Then the
that
second
one?
one should not be 0.000. That is not the p-value.
Yes, yes,
All right, thank you.
yes. Thank you. This one is your chi-square value. I don't think you need to. Most times you don't need to report it, except you're doing well in some projects. It depends on the people. Some people want to see like for people that are in statistics field, they want to see the whole process of your getting that value. So they will tell you to still bring up that chi-square value. But most times, all you need, like you said, is your p-value and your level of saving country 0.05. Okay,
Thank you, ma'am.
you're welcome. Okay, so we already established that an independent sample T test compares the means of two independent groups, and more or less the two group differ in their average score. Okay, and it has to more or less be one categorical variable and one scale variable, and the groups have to be independent group, not dependent on each other. That's like male and female. What it means that it's not dependent, that two people cannot be a male and female, I guess. Like you can't be like, that's the conventional thing. You can't be a man and a woman at the same time. You're two people. So like the groups are independent. Okay. So the same thing. It doesn't change the null hypothesis that the male and female radiographers differ in radiation safety knowledge scores. The null hypothesis say that no, they don't differ. There's no difference in their radiation safety knowledge scores, that they are equal. While the alternative hypothesis would assess the research question and say yes, there is a difference in their scores. Okay. So basically, we'll see it on SPSS now. You go to analyze, you go to compare means, then you go to independent sample t-test. Okay, so let's do that. Analyze, compare means, and independent sample t-test. Okay, so the first question I have here is okay, we can use this one. Do radiographers who received radiation safety training have higher knowledge scores than those who did not? Did radiographers who received radiation safety training have higher knowledge scores than those who did not? So that means what we're comparing is, what we are trying to find a difference is that people that said yes, they had radiation safety training, and people that said no, they don't have radiation safety training, do they define their knowledge scores because they've taken their knowledge scores? So now this place that says test variable, it's your skill, is your skill data, which in our case is our knowledge score, because that's the variable that is being tested. They're trying to test their knowledge score. So we're going to put our knowledge score in our test variable, right? Then the grouping variable is your categorical data. And in this case is radiation safety training, right? Yes, because it goes by name grouping. You're grouping them into people that said yes to this, to taking the safety training, people that said no to taking the safety training, right? I've already basically defined the groups, so I don't think I need to do that again. Options, 95% confidence interval, that's 0.05 level of significance. I don't think I need all these things. Okay. Why is my this thing not doing? Sorry, maybe I really do have to define group. Okay, let me define the group. Group 1 value is yes, and group 2 is no. Okay, so now it accepts me. Happy for it. Okay, so it says okay, and we try to see. Sorry, 1 second. Here's my okay. Okay, so what do we have here? Okay, so he also does a statistic for us basically. 87 people said yes, 33 people said yes, like we saw it before. It shows us the mean of people that said yes. That's their mean score. So the average that it takes is their knowledge score. Remember that we had, sorry, let me move this thing. I think people are seeing it. The average that we had was their this thing that we had was their mean score, was their knowledge score, which let me show you what it looks like in the Excel form, which is this more or less. So what it does is that it takes the average of the knowledge score of the people that said yes and the average of the knowledge score of the people that said no. And of course, their standard deviation and their standard error mean. Okay, so now the part that is important is this part. Now, SPSS will show you two, where equal variance is assumed and where equal variance is not assumed, right? And the part that we are looking at is where equal variance is assumed. That's this first part. Now, first of all, if equal variance is not assumed, you're not even supposed to do a t-test on it, because it's not a that one is now a lot of statistics. It's not a normally distributed data, and you don't do this kind of test on things that are not normally distributed, like whatever. Anyways, that's side gist. So we're concentrating on this first line of data, and we have our f value because the simple test, distinct test. Then we have our um this value. So we have our t-test value and our degree of freedom, which is this. And once again, our focus, what we are going to be reporting is this particular value, this significance to tail test, because that was the test that was conducted. So we go back to what our hypothesis was. Remember, our null hypothesis said that that radiography safety training, or rather, people that the radiographers we received, how do we put that in English now? The question says, do radiographers who received radiation safety training have higher knowledge scores than those who did not? So we are saying that no, radiographers who received radiation safety training, that's what the null hypothesis is saying, do not have higher knowledge scores than those who did not. That's what it's saying. Meanwhile, the alternative is saying that radiographers who received radiation safety training have higher knowledge scores than those who did not. So it's saying the opposite. Now, the same rule applies for this, which is basically the rule that applies for most test statistic. When your p-value is less than your 0.05, most of them, you reject the null hypothesis. But when your p-value is greater than 0.05, then you fail to reject the null hypothesis. Do we get? Okay. So we started late, Charles. What there's already 8, but we started late. Okay, so your p-value, our p-value here is 0.00. Now we are getting this kind of perfect score because this data was generated. So it was almost like generated um to get, like, generated so that it reflects what reality looks like. Now sometimes, like I was saying before, when you that's in the last class, when you give your questionnaire or try to collect data, especially when you give out questionnaires and maybe you don't like sit down to get the answers from the people do all sorts of things with questionnaires, just tick whatever because they don't want to feel it. So you might get a little bit of things that are not correlating. You're like, oh, what's happening here? Anyways, that aside. So P is 0.05 and it is less than, sorry, P is 0.0 and it is less than 0.05. So we are rejecting the null hypothesis. And the null hypothesis says that those who received radiation safety, those who received radiation safety do not have higher knowledge scores than those who did not. So it's a negation. So we're rejecting that happened. So what we're basically saying that those who received radiation safety have higher knowledge scores than those who did not. Now, what I'm not sure is what informed this knowledge scores. What was calculated to get knowledge scores? Because that might help us to know whether we're getting a true result. Maybe what they used to check this knowledge scores was things on radiation safety. That's why it's showing that it's the scores do differ. Yeah. But if it was something else that they used, maybe I don't know, they used knowledge of how to use the equipment properly or something, maybe that won't reflect that way. Okay. So that's for independent sample t test. And basically that's what that's what the interpretation looks like. That's basically what you collect from here, the 0.01. So I tried to look at what's the English I use now? Just get a sample of basically how it can be reported on this my Google form, this my Word document. So it says that this is not the same. I don't think it's the same data. It's not the same data. This is just the and we can try to do something like that for this one that we just got now. So it says that male radiographers, their mean being 78.6 and their standard deviation being 6.2, has higher radiation safety knowledge scores than female radiographers, with their mean being this and their SD being 7.5. Um, Levin's test was not significant because it was 0.37, indicating that the assumption of equal variance was met. Okay, so I didn't see that. So another thing to check, which I just assumed, was that when your living tests, this significant value of living test is here, is not very important because, like I said, you already automatically calculates it if equal variance is assumed. But for the sake of knowledge, if this your significance value here, this one that I'm trying to, I don't know if you're seeing it, where you have sorry, where you have 0.428 under Levin's test of equality of variance. Because what t-test does is first test equality of variance. It says that the equality of variance for the two groups that you've put before it now goes ahead to do the t-test proper. So when it has the equality of variance, it can now go ahead and conduct its t-test. So this what checks what in when somebody is manually doing a t-test, they would first check for equality of variance, and this is kind of value they will get. Now it's compared to the same 0.05. Now if um was the it's the same thing. HO for that's your null hypothesis for your Levin's test. I feel like I shouldn't say this because it's going to confuse us. But anyways, HO for your Levin's test to be that there is no equal variance assumed, right? No equal variance is assumed. Is that what it is? Yes, that no equal variance is assumed. But the null hypothesis will be that equal variance is assumed, right? So now if p-value is less than, if your p-value is less than, like the same thing, if it's less than 0.05, then you reject no hypothesis. But if it's greater, you accept no hypothesis, which that your Levin's test, that's your equal variance is assumed. So let's go back to this document now. So Levin's test was not significant, and indicating the assumption of equal variance was met. Therefore, the equal variance assumed rule was used. The independent sample test shows that a difference in mean knowledge score was statistically significant, which is this, and p-value is 0.05. Since the p-value was less than 0.005 was less than 0.05, the null hypothesis was rejected. So we conclude that male and female radiographies differed significantly in their radiation safety scores. So in our case, if we do this write-up, I think I will do this test on our own, and I'll send in the assignment question tomorrow morning. I already have it. So if we do this test and we do the interpretation, our own is going to end that since p-value is equal to 0.00 and sorry, yes, and level of significance is 0.04, then the null hypothesis was rejected, and we conclude that the radiation safety training differs like the radiographers who received radiation safety training have higher scores than those who did not, more or less, or differed significant, or rather, people who said yes and no to radiation safety training differed in their knowledge scores, something like that. But either way is just making a way that you can explain, or rather, it's simple to understand to you and to the person that reads your work. Okay.
Yes,
So
please.
I don't know whether
Excuse me.
there's any need.
Sorry.
Oh, sorry. Yes,
Mm.
yes, yes.
Can you get back to the document where you
Was
read now?
writing. Okay.
Yes, the
Yes.
write-up.
Mm-hmm.
Okay. I know you said you don't want to talk about it, but it looks like you say you're giving us an assignment. You're supposed to report like this. This
Okay.
living test, he said
Yes.
living test was not significant. P is equals to 0.637. My
Mm-hmm.
question is, at what point will it become significant? So that means it's not following the same as P, our normal P of 0.005, because
Okay. It says that
0.03 is more. Okay, go ahead. At what point does it become significant and what's the implication?
so we are still comparing our living test with 0.05, right? you still compare it with that level of because that level of significance that you use in your like once your data says that, oh, this is your level of significance 0.05. So let's try to analyze, and with my pen and paper, the Levin's test gave us that our p-value is 0.367, right?
Mhm. Okay.
0.367. And we had said that if your p-value is less than 0.05, then you reject the HO, the null hypothesis. But if your p-value is greater than or equal to 0.05, then you accept the HO, right? That's what we said. Okay, so now um um for our Levin's test, what we are trying to find is that does this data set have equal variance or does it not have equal, like can equal variance be assumed here, or equal variance, the assumption of equal variance is not met here. So what so that means our null hypothesis here would be what? It would be that equal variance cannot be assumed here, right? I want to know whether we're on the same page. Is that what is going
Okay.
to be?
Yes, but here it's small, and it said that it was met. It said indicating the assumption of equal variance was met.
But this is 0.367. Oh.
It's more than 0.05.
Yes, that's your accepting HO.
Okay, because HO would have been that it was. Oh, okay. Thank you. Beautiful. I think it's clear now. Very clear. All right.
Right. Okay. So basically, that's basically it. It's supposed to be 1 hour. It's the 1 hour class. It's just how do I interpret my chi-square and how do I interpret my sample t-test? When do I use a chi-square and when do I use a sample t-test? So is there any other question? I think I'm done actually. Let me stop presenting. Sorry. Is there any question? I mean, them two people have not said anything since. Alan and I don't know whether I pronounced that well. And Olagunju.
Yes.
Okay, so everything is clear. All right, thank God. Okay, so I would send the assignment to the group tomorrow morning. No, it's not difficult at all. SPS is not that hard. I'll send it, and the deadline can be, since the next class is on Sunday. Hopefully, Chijoke would confirm that. Yeah, I think deadline can be on Friday, but I'll send it tomorrow morning. Okay.